Hello.
Hello.
Yeah, can you hear me?
Yes, good afternoon.
Yeah, good afternoon. Okay, so we'll continue atomic structure. We discussed the basics yesterday and we'll look at the different models that were discussed or discovered by the scientists today. So we saw yesterday about Rutherford, about J.J. Thomson discovering electrons and all, right?
Yeah,
That was through the cathode ray and all, and he put a voltage and he saw small charged particles coming out of every different types of metals, right?
yeah,
Basically, that told him that all of these different metals carried the same subatomic particle, right? He
yeah,
called that particle the electron, and those particles had negative charge. So that also implied that there must be some positive charge in the metals also.
yeah,
Because usually when he saw the metal, it was neutral. So if negative charges are coming out, then there must be also positive charges somewhere, right?
mm,
So that was Thomson's understanding. That then he thought that okay, there could be positive and negative charges interspersed with each other like this, right?
yeah,
This was what he thought of the atom as, but then this was disproved by Rutherford's experiment, which was the scattering experiment, right? So what happened there was he took a very thin gold foil. So basically, it's like a very thin sheet of gold, right?
yeah,
And that sheet of gold has been taken because uh, if you have a thin sheet, that will still have hundreds of layers of atoms actually, right? You want to
yeah,
keep it as thin as possible, and then you are firing towards it, you are firing alpha particles, which are helium nuclei. Do you know what alpha particles are?
yeah,
So basically, it is helium is usually written as 42He, right? So,
yeah. So it'll be 2 plus.
so it is helium 2 plus actually. It has lost the two electrons, so it is just basically the nucleus of the helium atom, right? So
Yeah,
helium 2 plus is basically known as alpha particles, and many alpha particles were sent towards this gold foil, right?
yeah,
Now, the obvious assumption is that if whatever the results here, we'll try to understand that. What he found was almost 95% went through undeflected. 95% of the alpha particles went through as if they faced no obstruction at all, right?
mm,
Some of them were deflected a little bit, some of them were deflected by big angles, and some even came back,
yeah,
right? But these were very few, like a few of them got deflected by a large angle, right? And very few of them directly got repelled and turned back, right?
yeah,
So from this, he understood, Rutherford, that if the atom has positive charges, it is positive charges that can repel the helium positive at nucleus, right?
mm,
So the big repulsion that you are seeing sometimes, it must be due to the positive charges, right?
yeah,
But most of the time, for most of the rays, you are seeing no effect, right?
mm,
So that means they are passing through without any barriers, undeflected, right? Most of the rays.
yeah,
So that means most of the atom is not providing any repulsion, no?
mm,
Which led him to make the statement that the atom is mostly empty space and the nucleus is occupying a tiny dot in the middle, right?
yeah,
This is a typical atom, mostly empty space. Nucleus is a tiny dot in the middle with positive charges, right?
yeah,
So all the mass of the atom is concentrated at the nucleus and it has all the protons and all the neutrons. So if an alpha particle is unfortunate and it is coming straight towards the nucleus, then it will be clearly stopped and turned around because the electrostatic repulsion will become very strong as it comes closer. No?
yeah,
repulsive forces will be there between helium-2 plus and this nucleus, right?
Yeah. Because KQ1, Q2 by R square.
Right.
All
That
are
force will
really,
become very big because R is becoming small.
yeah.
And basically, uh, it will get repelled and you will have to turn back, right? Go back like that.
Yeah.
Correct. So that is the reason why he said that most of the charge and mass is concentrated in the nucleus, but most of the other part of the atom is empty. The electrons are roaming around there, but that doesn't block any positive particles from moving, right?
Yeah.
Because they will actually be attracted, no? So it will easily go through there, right?
Hmm.
So basically, that's why the results came like this. Very few of them got deflected, and most of them passed through. So according to Rutherford, the model was a planetary model, right?
Yeah.
All the positive charges and entire mass almost is concentrated in the nucleus, and electrons are going around in planetary type orbits. Correct?
Yeah.
Okay, 1 second, just hold on. I have to make a call quickly. Okay, so what I'm saying is this was Rutherford's model. Now, there were problems that were discovered with Rutherford's model quite pretty soon. Okay, do you know what are the problems of Rutherford's model?
So there was this guy,
Hmm.
Maxwell.
Hmm.
He told that any charged particle that's accelerated
Hmm.
will lose energy.
So basically, this is one of the main theories of Maxwell's electromagnetism. So in 12th grade, when you learn physics, you will learn multiple laws like Gauss's law and Ampere's law and stuff, right? And all of those laws were combined in one major idea of electromagnetism. That was Maxwell's electromagnetism, four laws. Okay. So if you want to look at it, you can look at chapter 40 or 41 in HCV. I think 40. In HCV volume 2, right? You have the book, right?
Yeah.
So Maxwell's laws in that is a major foundation of all our physics. So Maxwell's laws is always correct. Okay. So that is without doubt, it has been experimentally checked a lot of times. Okay. So that law predicts that any charged particle will radiate energy. Any accelerated charged particle, right,
Hmm.
will give out electromagnetic waves, will radiate EM waves. EM waves is basically just like light, right?
Yeah.
So if you have accelerated charged particle, it will radiate EM waves and therefore it will lose some of its energy, right?
Yeah.
Now, if you think of the atom in a planetary model, the electrons are going around in circles, right?
Yeah.
But if you are going around in a circle around a central nucleus, then automatically you are constantly accelerating, right?
Yeah.
Because of circular motion, always there is acceleration, no? Because direction is changing for the velocity, right?
Hmm.
So if you are constantly accelerated and you are a charged particle like an electron, then you should constantly give out electromagnetic waves, right?
So
Hmm.
This is not related to chemistry,
Hmm.
but in circular motion, there are two types of accelerations, right? One is tangential and
Hmm.
one is centripetal.
Hmm.
And then there's angular acceleration also.
Right. So angular acceleration is just another way to describe the same thing. It's not like unrelated. So, for example, tangential acceleration AT is equal to R alpha. Right?
Ah,
The AT and alpha are same thing actually. They are describing the same thing.
but then we say that the
Hmm.
direction of angular acceleration is like perpendicular to the plane.
Right, because otherwise your maths won't work because the tangential acceleration has to be like this, right?
Yeah.
See, it is actually the reason you are getting confused is because you don't know the cross products and all. Like it is V is equal to omega cross R. Like the result that you remember like this, right? This result you have seen, right?
Oh, acha.
L is equal to R theta, you would have seen, no?
Hmm.
This is arc length, this is theta, and this is R, right?
Ah, that
And
was
you would
great.
have differentiated and learned that speed is equal to R into omega, right?
Yeah.
It's not so simple like this. This is what students are taught. The real relation is this. What this means is you want velocity to be a vector, right?
Yeah.
And if you think of circular motion, think about it, the velocity is along the tangent, right?
Ah, so it'll be for
If you have a radius vector, think about it. How can you make a radius vector combine with something and give a tangential vector, right?
hmm.
This is the left hand side, no? So you have to combine one vector with another something and you should get an answer as a vector. So it has to be a cross product, right? It cannot be dot product.
Yeah, otherwise you'll get a scalar.
So answer, this has to be called a vector now and this has to be a cross product now, right?
Ah,
If that is the case, then the direction of omega has to be fixed to be perpendicular to the plane by right hand thumb rule. Think
acha,
about
हाँ,
it.
हाँ, हाँ, I got it. So
Agar
you,
your fingers are curling like this, then thumb is pointing in the direction of the omega. Because then, if if you think of XYZ axis, this is Z, right? This is X,
okay,
this is Y, right?
yeah,
So now think about it. The radius vector is I cap, right?
hmm,
And if your omega was K cap, for example, right? Correct?
हाँ,
So then you would have to do K cross I here, right?
hmm,
K cross I is positive J.
yeah,
And you need velocity to be positive J, right?
oh,
You understand how the direction of omega was set. Now, in
oh,
books and all, they might tell you that if it is anti-clockwise rotation, you
then it'll
will say
point out.
that it will point outward, right?
Yeah,
Correct. So the reason for this is this right hand thumb rule, and the reason is because you need it to be a cross product like this. If you don't put it as a cross product, if you, for example, put it like this, right, then you will get the wrong answer for the direction of the tangential velocity.
it'll be in the opposite direction.
But it should be in this direction, it will turn out to be this way, which doesn't make
Yeah,
any sense.
hmm,
If the rotation is like this, it is common sense that the tangential velocity is like this, right?
yeah,
The only formula that will fit is this, not this. Do you understand?
yeah,
So now if you differentiate this result, then you will get A is equal to alpha cross R and all, AT.
hmm,
So the reason alpha vector is out of the plane is because the omega from which it comes is also out of the plane, right?
yeah,
Do you understand what I'm saying?
yeah, I got it.
So that is the reason. But ultimately, in circular motion, the acceleration is basically because the particle is changing direction at every moment, right?
Yeah.
This acceleration has two parts. There is a part like this towards the center, and there is a part like this, which is tangential. The net acceleration could have two parts in circular motion. The AC is also always v square over r, right?
Yeah.
The AT will be the rate at which the speed is changing, the magnitude of AT.
Yeah.
If the speed is not changing, then if the speed is
Yes.
not changing, then there is no tangential acceleration,
Um,
right?
there is no direction change. Like the magnitude would be the same.
No, what I'm saying is the direction is already set. I've already shown you the two directions.
Oh,
I am
okay.
right now telling you only about the magnitudes of them.
Then 80 would be 0.
If speed is not changing, then you call it uniform circular motion, right? In
Yeah.
that case, AT will be 0, but AC is still not 0, right?
Hmm.
Because even if it is uniform circular motion, it is still circular motion and it's always accelerated towards the center, right?
Hmm.
If it
Yeah.
was non-uniform circular motion, it will have both the components of acceleration, right?
Yeah.
It will have AT also and it will have AC also, and resultant acceleration will be something like this for non-uniform, right?
Yeah.
For uniform, the resultant acceleration is always just towards the center,
Hmm.
right? But if
Yeah.
you really want to understand everything properly, then what you need to do is chapter number 6, circular motion, HCV, first 2, 3, 4 pages. The way to understand the theory is by going through HCV, okay? Just by looking at your Allen module or whatever coaching modules and all won't help you that much. If you go through HCV, you'll understand everything clearly. So that is what I would recommend you should do. Okay.
Okay.
Is it understandable what I'm saying?
Yeah, I understand.
Okay. So in the atomic structure, because of Maxwell's law, it was predicted that charged electrons will always keep radiating EM waves, right?
Yeah.
Because there is going around the nucleus. That was the Rutherford's planetary model, right? Now,
That
if
was,
that is the case, then automatically it will lose energy all the time, no? Electrons,
yeah.
correct? And if
Hmm.
they lose energy, they will come closer and closer to the nucleus and fall into the nucleus very quickly.
Yeah.
It's like you are throwing a stone in the air and trying to make it go around as much as possible, go in the air as far as possible. But as the stone loses energy, it will fall, no?
And then it'll spiral down. Yeah.
So technically, like as soon as it loses energy, it has to come to a lower orbit and all, and slowly it will come to the Earth, right?
Yeah.
So the point is that here the electron would also collapse into the nucleus and the atom would not be stable, right?
Yeah.
But actually, when you see the real atoms, they are quite stable. There is no issue. They are existing for billions of years, right?
Hmm.
So then there must be a big problem with Rutherford's planetary model. There is a problem, something, right?
Hmm.
So that's why now we have to look at something else which fixes this issue and explains how atoms are stable, right?
Yeah.
It should not be like a model which cannot explain Rutherford's scattering experiment. So it has to maintain the explanation of the scattering experiment, right? That the atom
Yeah.
is mostly empty and stuff like that, right?
Hmm.
But it should also not have the problem that atoms are collapsing. In Rutherford's model, it's collapsing, right?
Yeah.
So that is where we get Niels Bohr, and he is one of the founders of quantum mechanics, and he came up with a model which is like, it is like a slightly different type of thing, and it's a leap in logic. You have to appreciate what he's saying. So he said that electrons, almost everything was same as Rutherford's model, but he added two, three things. Okay.
Mm.
So assume everything in Rutherford's model is roughly same. Everything in Rutherford's model. He said electrons are moving around in orbits and all, and nucleus is small and tiny at the center. But he said electrons can only move in certain orbits. Do you understand what I'm saying?
Yeah.
It's not like any orbit is fine. Only certain orbits are allowed orbits, right? Other orbits are not allowed, right?
Mm.
So there will be some orbit here, then there will be some orbit here, and then there will be some orbit here. Only those are allowed, right?
Yeah.
Then, when an electron moves in an allowed orbit, moves in an allowed orbit, it does not radiate energy. So basically, he's taking very big liberties, and he's just saying that Maxwell's laws have been switched off. Do you understand what I'm saying?
Yeah. It should radiate
It
energy.
should radiate energy, but Niels Bohr is saying that if you are moving in the allowed orbit, it does not lose energy. It does not radiate energy. So his solution is like a uh, very weird solution where he's saying, "Hey, let's switch off the laws. Maxwell's laws don't work in this particular situation." Do you
Mm.
understand?
Yeah.
Rutherford's problem was that he could not explain that, no? But Bohr's is saying that if you are in the particular orbit, then it won't lose energy. So there is no problem only. Okay. And what is
Mm.
so special about this orbit? He also said a third thing. Which orbits are allowed? Orbits where the angular momentum mvr is an integral multiple of h by 2 pi. Do you know angular momentum mvr?
Yeah.
So if you are in an allowed orbit, always your angular momentum will be some integer multiple of this quantity h by 2 pi. Okay. So
Mm.
this is a major contribution because this tells us which orbits are allowed, which are not allowed, right?
Yeah.
If without saying this, it's all just description, and he's saying Maxwell's laws have to be cancelled, right? But because he said this and he has figured this out, now you can actually figure out which orbits are okay, which orbits are not okay, and you can try and do things with it. It's not total like randomness, he's saying. Do you understand what I'm saying?
Yeah.
Because otherwise it feels like you are saying the same thing as Rutherford, and you are saying that let's not worry about Maxwell's laws for a moment, right?
Yeah. Uh,
But he has not just said that, he has also said something special, that only those orbits are allowed where MVR is equal to NH by 2 pi, right?
mm.
So now let's see what are the consequences of this. First of all, notice that it doesn't have the problems of that atoms are collapsing and all, right? Because here the electrons are always moving in orbits where they don't radiate energy, right?
Uh,
Are you understanding what I'm saying?
yeah. I'm just wondering how this MBR came. Like,
How
how
this
do we,
MVR came?
like, why is it integral multiple of h by 2?
Oh no, that you can't understand. So you cannot wonder about that so much. You can't understand it from anything in classical mechanics. Okay. The only way to understand it is via quantum mechanics, which right now you don't know. Okay. So Nothing in the mechanics or physics that you have learned so far can prepare you for this. So,
Oh,
so there is no point in wondering also. The physics of it is totally different, and you will learn about it in your first year in college. Like we had a course in quantum chemistry first semester. So the details of that you will learn only later. So don't worry about it right now. Okay. So I will try to explain in brief what is the Schrodinger model and all. But first, before we go to the quantum mechanical model, the Schrodinger equation, we have to understand what is the predictions of Bohr's model. What is it saying, right?
yeah.
So what we will do is we'll do the mathematical description of Bohr's model. So think about it. This is the nucleus, and these are the orbits. These are the allowed orbits, right?
Hmm.
Electrons can only go around in allowed orbits, right? Now
Yeah.
imagine a particular electron in a particular allowed orbit. What you can say is, why is it going around the nucleus? Because of the Coulomb force of attraction, right?
Yeah.
And let's say it is going at a speed of v and the radius of the orbit is r, right? Just like
Hmm.
in physics, you can say centripetal force should be mv square by r, right?
Yeah.
The centripetal force is the Coulomb force of attraction, correct?
Yeah.
Now, let's think about the Coulomb force of attraction. The nucleus will have a charge of plus Z times E, right?
Yeah. Because those many proton.
Uh, Electron has a charge of minus E, right?
Yeah.
So the magnitude of this attractive force, Coulomb force, is going to be K ZE times E by R square.
Ah.
That should be equal to the m into v square over r, the acceleration produced by it, right?
Yeah.
This is like a circular motion physics equation, right?
Yeah.
Okay. Next thing is, we also have that while you are in this orbit, angular momentum of the electron, which is actually r cross p, so technically it is r cross mv, but r cross v, r and v are perpendicular to each other, right? Do you see this?
Yeah.
R and V are perpendicular to each other, so the angular momentum will have some k cap and all. Some it will be perpendicular to the plane, the vector, right?
Hmm.
So we don't have to worry about the vector sign. The overall angular momentum will simply be mvr, right? Magnitude,
Yeah.
right? That mvr should be nh by 2 pi according to Bohr's model, right?
Yeah.
So these are the two equations using which we can derive everything that we need. Okay. So we'll just see how, and you need to know this derivation. So do you understand what the equations are?
Yeah. One
This
is the
is
fourth.
one is the force equation, other is Bohr's postulate. Bohr said
Ah.
that this is the only possibility for allowed orbits, right?
Yeah.
Now notice this is kz e square pi r square is equal to mv square by r. So we will cancel one radius here, and we are getting kz e square is equal to mv square r, right?
Ah.
And notice from this equation you have mvr is nh by 2 pi, right?
Hmm. You can substitute.
We can divide, right? We can divide the two equations, right?
Yeah.
We will be left with v only, no?
Hmm.
So we'll get v is equal to kz e square by nh by 2 pi, right?
Into. Ah.
So velocity of the electron is coming out to be 2 pi k z e square by nh. Do you understand?
Yeah.
Great. That is a very important result. We will see the value of it soon. Now, if you have found the velocity, the next step is, can you find the radius of the orbit, right? I
You know
have
the velocity t, so you can substitute it in
in second
MVR.
equation, right? So we can say MVR is equal to NH by 2 pi. Therefore, R is equal to NH by 2 pi MV, right? So R is equal to NH by 2 pi M, and let's put for V 2 pi K ZE square and on top NH, right?
Yeah,
So you'll get N square H square by 4 pi square MKZE square. Correct?
yeah,
So you're getting this as the radius of the orbit also, right?
yeah.
Now think about it. Can we find the total energy of the system while this was all happening, while electron was moving around in the orbit, right? So we can actually, what you will say is kinetic energy of electron plus potential energy of the whole system, right?
Hmm.
That should give me total energy, no?
Yeah,
Correct? Now, in gravitation, in physics, you might have seen that potential energy is minus g m1 m2 by r.
yeah.
Two masses separated by a distance r, the potential energy is this, right?
Hmm.
If you don't know this, then you need to revise your physics of
No, no,
gravitation and all.
no, I know, I know.
So similarly, because the two laws are so similar, Coulomb's force and gravitational law, similarly for Coulomb force also, the potential energy when you have multiple charged particles will be given by the formula K Q1 Q2 by R. The reason we are not having plus or minus sign here is because the sign is taken care of in the charges itself in Coulomb's law, right?
Acha, okay, so if it's attractive, then it'll be negative.
If it is attractive, it will be negative. If it is repulsive, it will be positive. Just
Hmm.
like in the Coulomb force, the charge sign itself takes care of the direction of the force, right?
Yeah.
But in gravitation, we have to say that it has to be negative sign because masses can never be negative, right?
Ah,
So just like that here, when you have minus g m1 m2 by r was the potential energy in gravitation, this is the potential energy in electrostatics, k q1 q2 by r.
hmm.
The reason it is so similar is because the law is so similar. G m1 m2 by r square and k q1 q2 by r square, right?
Yeah.
So what you have to do for total energy, potential energy will be for the whole system. You will say kinetic energy will be half mv square for the electron plus potential energy will be k q1 q2 by r, right?
Hmm.
And notice that this will come out to be negative, right?
Because proton and electron.
Because it is the nucleus and the electron, not just a one proton, right?
Ah,
It is plus ZE and minus E, right?
yeah.
Also, notice that velocity can be written like this 2 pi k E square by h whole thing multiplied by z by n, right?
Yeah. Yeah.
The reason I'm writing it like this is
But-
everything inside the bracket is a physical constant.
Yeah.
2 pi E is the charge on electron, H is Planck's constant, K is the Coulomb's constant, which is 9 into 10 power 9, right?
Hmm.
So it will be convenient to not try to remember the whole formula. You can just calculate all of these constants and remember it as the value of this constant and multiply it by Z by N, right?
Yeah.
Z by N will tell you which orbit you are looking at. N is 1 is the first orbit, N is 2 is the second orbit, and so on. And
Hmm.
Z is the atomic number of that particular atom. Correct?
Yeah. Yeah.
So if it is hydrogen, I would do 1 by N. If it is helium, I would have done 2 by N.
Hmm.
So that is your Bohr's model prediction for velocity. Similarly, you can also say that here h square, 4 pi square, mk, and e square. All of these are constants of nature.
Oh.
M is the mass of an electron, K is Coulomb's law constant, E is charge of electron, H is Planck's constant, right?
Hmm.
So the formula can be written as R is equal to some constants into n square by Z, right?
Yeah.
Do you understand?
Yeah.
Here it was V is some constants into Z by, correct?
Hmm.
Here it is R is some constants and n square by Z, right?
Yeah.
Notice the reason I'm not putting the constants right now is because I don't want to keep using the all of these constants every time again, because it turns out that you will get similar expressions for kinetic and potential energy also. You can use the original expressions and see what comes. So for example, I will have to create space here only and do it. So let me just find kinetic energy and potential energy once. You will see how they are both similar. Kinetic energy will be simply half mv square, right? So use the formula for V and find the kinetic energy of the electron. Half m v square, v square. So see, V is in this, right? So it will be 4 pi square k square z square e power 4 by n square h square.
Yeah.
So notice here that you are getting half into m into 4 pi square k square e power 4 by n square h square and z square, actually n square I will keep outside, z square by n square, right?
Hmm.
All of the stuff inside is a constant. Can you see?
Yeah.
And see, kinetic energy is dependent on z square by n square, which makes sense because velocity was dependent on z by n.
Hmm.
You understand?
Yeah.
Potential energy. That would be K Q1, Q2. Q1 is ZE, Q2 is E, right? With a negative sign, correct?
Yeah.
By R square. But R square is this expression. If you square it, it will become N power 4, H power 4, and divided by, no, I'm making a mistake. It is not R square.
It's
K Q1,
only.
Q2 by R, right?
It's only by
So it
R.
will be just n square h square, and on top you'll get 4 pi square mkze square, right?
Hmm.
So now see what is coming. Minus 4 pi square m is there, k square is there, e power 4 is there, see, by h square, and then z square by n square. Can you see
Hmm.
what I'm saying?
Yeah. Kinetic energy is half of that.
So see, this constant is exactly same, and kinetic energy is just half of that. Same constant is present here also, but it is negative now, right?
Yeah.
So you can technically see that kinetic energy is equal to negative potential energy by 2,
Hmm. Yeah.
correct? So potential energy is basically negative 2 times kinetic energy, right?
Hmm.
So total energy is becoming, if potential energy is negative 2 times kinetic energy, total energy is negative of kinetic energy, okay?
Yeah.
Do you understand what I'm saying?
Yeah. Yeah.
So total energy is the negative of kinetic energy, and kinetic energy is always positive. So total energy will come out to be always negative, right?
Ah.
And this is for a hydrogen type atom, where this is for any atom where the electrons are inside the atom and they are bound. So this is one important idea that you need to realize, that when an atom is in a normal state where nucleus is pulling the electrons and electrons are going around the nucleus in a normal situation, then the electrons are bound to the nucleus, right?
Yeah.
It is not free to move out wherever it feels like, cannot escape the atom, right?
Hmm.
You are bound to the nucleus, and therefore total energy of this bound system will always come out to be negative. Total energy
Yeah.
is coming out to be negative of the kinetic energy. It is kinetic energy of electron plus potential energy of the whole thing.
Yeah.
So remember always that for bound systems like an atom, like Earth and its satellites in gravitation chapter also, the total
Uh,
energy will always be negative.
uh,
The only way total energy will be positive or greater than zero or zero is if the body has escaped to infinity. So
yeah.
if the satellite has to escape to infinity, it has to go away from the gravitation of the Earth, then you have to give it enough total energy so that its total energy is greater than equal to zero. If you give it not enough energy such that its total energy is still negative, then it may go very far, but it will come back to the Earth.
Yeah. And an elliptical.
It may go into an elliptical or hyperbolic orbit also, but it will have to eventually return because its total energy will become zero at a finite point, not at infinity.
Uh,
So that is mostly physics, but right now I just wanted to mention it because it connects a lot of things in gravitation also. Okay, so you need to know it. Here in atomic structure, what you need to now remember is you need to know the derivation. The derivation came from here. Kze square by r square is equal to mv square by r, and mvr is nh by 2 pi. Both of these together gave us velocity, gave us radius, and from there we found kinetic energy and potential energy, right?
yeah.
Correct? You should do the derivation yourself once and see if you're able to get a v and r and everything yourself or not, right? But the
Okay.
thing to remember is the V expression comes out like this. All the constants can be evaluated and you can remember the value 2.18 into 10 power 6 meter per second multiplied by Z by N. Do you understand what I'm saying?
All the constants came out.
All the constants multiplied and came out to be this. Okay.
Hmm.
The radius will be 0.529 angstrom. Angstrom means 10 power minus 10 meters into n
Hmm.
square by z. Do you understand what that means? All the
Uh,
big numbers, no, nh by whatever, right? All of it multiplied together comes out to be this, right?
uh,
And the energy, total energy, remember that it was negative of kinetic energy, right? Total energy came out to be minus 13.6 electron volt times z square by n square.
acha, uh,
You know, 1 electron volt is 1.6 into 10 power minus 19 joules, right?
hmm.
So this total energy came from the same expressions, what we did that derive previously, right? Nothing weird. But we have calculated all the numbers, okay?
Okay.
And this is important to remember because in problems, it is but much easier to use these formulas, right?
Yeah.
Much easier to use it, also to remember it because it's so simple. You just need to remember three numbers, correct?
Yeah.
So that is your consequence of Bohr's model. Now, what you need to do is now read up the atomic spectra part and start looking at the Schrodinger wave equation and the slightly more advanced stuff. We will discuss the problems with Bohr model and atomic spectra. Okay, first we'll have to discuss the success of Bohr's model, right? The major success, why everyone believed him, was because of this total energy expression, which explained atomic spectra. This equation that we have derived, no, this
हाँ
explains those Balmer, Rydberg, Bastian, bracket, Lyman lines, absorption and emission spectra lines. If you don't understand that, you need to read a little bit from the book. Okay. You
I
have
read.
seen that Balmer Rydberg equation, no? 1 by lambda is equal to rz square, right?
Yeah. R Z.
1 by lambda is equal
R
to some constant into 1 by n square into minus 1 by n square, right?
हाँ that.
That equation, when it was first discovered, that equation had no explanation.
हाँ, it got like through experiments they found that out.
Right. So people had a lot of experiments and a lot of wavelengths in absorption and emission spectra. And one school teacher just figured out the formula by tinkering with numbers.
Oh,
The formula was discovered much before. Formula was available and everybody used the formula, but nobody knew why it is working
हाँ.
for 30, 40 years almost. But after Bohr's model, now you can explain the formula with logic. So you
With
need to
Bohr,
read. Tell me.
with Bohr's mod, I thought it was like in some orbit, this much energy will be the
But
second.
Bohr's model gives the energy of the orbit, no?
Oh, अच्छा, we can just.
Is Rutherford giving us energy of the orbit?
No.
Rutherford did not know the radius of the orbit. No, MVR is equal to NH by 2 pi, he didn't have,
हाँ.
right? So he is stuck with one equation only, right?
Hmm.
But Bohr has given us total energy of every orbit, no? Now notice that if you subtract the difference between two orbits' energies, you will get 1 by n square minus 1 by m square.
You'll get the energy required to go from one orbit
And
to
that
another.
is the wavelength that you see, that if you equate it to hc by lambda, you will get the exact Balmer equation and Rydberg equation.
हाँ.
So if after Bohr, you were able to explain 30, 40 years worth of experiments, which were earlier working out according to a weird formula, but nobody knew why.
He explained.
Do you
हाँ.
understand what I'm saying?
Yeah.
So go through this part and understand why it was successful and then find out why it was not successful. What was the mistakes in it? What were the problems there? And that is where we come to quantum mechanics and slightly more advanced stuff. Okay.
Okay.
So read up that last part of the chapter, chapter 5 in the book that I have sent you. Right?
In that book you
Hmm.
sent, it's all like
Chapter
everywhere.
5 is what you have to start. Atomic
Okay.
structure.
Chapter 5.
The first
Okay.
four chapters are basics, although you should read them. Mole concept and all is there in the first four chapters. Mole concept, reactions in aqueous medium and all is there, right? Though
All. Hmm.
those are basic concepts which you are expected to know, but chapter 5 is atomic structure. That is where you need to start with.
Okay.
Okay. So go through that and we'll do a class during the week to try to finish up this part of the theory, right?
Hmm.
So we'll coordinate on WhatsApp and we'll decide some time on Tuesday or Wednesday, something like that. Okay.
Okay.
Okay, that's all for now. We'll continue in the next class.
Okay. Thank you, sir.
Bye.